Welcome ENET 130 Semiconductors at Bellingham Technical College. This lecture is about amplifier concepts. It's drawn from our Fiore Semiconductors Devices textbook, Chapter 6. It's a fairly short chapter, and it deals with concepts that are general to all amplifiers. Up till now, we've been concerning ourselves mainly with bipolar junction transistors, and we've covered concepts like a Q point, or a collector current versus collector emitter voltage drop operating point of the amplifier, or excuse me, of the transistor itself, and the amplifier circuit built around it. We've looked at DC load lines and looked at what the maximum collector current we can get if there's no voltage drop collector to emitter in our transistor, and at the other end of the load line, what the maximum collector to emitter voltage drop would have to be to stop all of our collector current. So we've already gotten used to distinguishing characteristics of our BJT, like beta, and characteristics of the circuit around it, namely our DC load line. We've also touched on biasing, and that's where we've started to introduce the concept of amplification of a signal. So remember, biasing is what we do to ensure that our forward bias voltage at our base emitter junction is satisfied, and we don't have to use our input signal, which may be much less than that forward bias voltage necessary to open the transistor and actually draw current and amplify the signal. So we've basically been touching on aspects of amplification in the context of bipolar junction transistors. So now we're going to pan back and we're going to look at some general characteristics of any signal amplifier, irrespective of the exact circuitry that's being used to accomplish the amplification. This is important because not all amplifiers use bipolar junction transistors. Most specifically, our field effect transistors that we have not studied and we're not are not going to deal with in the context of amplification in this particular course. Nonetheless, they can serve the same role as our BJTs, albeit with different circuitry. So this is general amplification concepts that we will then apply for small signal amplifiers in the context of our BJTs in Chapter 7. Okay. Signal amplifiers. We're going to go over some definitions that we're going to use throughout the rest of this course and our subsequent course or two in our ENET series. What do amplifiers do? They increase the amplitude, hence amplifier, amplitude, similar word for a reason. They increase the amplitude of a voltage or current without doing anything else, without changing the waveform, the phase, or the frequency, which are pretty much the only other things that are characteristic of a signal. So all we want to do is raise our V peak. Keep the waveform proportionately the same, don't shift phase angle, don't change the waveform. The extent to which we amplify, that we increase that amplitude, is known as gain. And we can define gain in terms of power, voltage, or current, and they're all related. So gain is generally defined as the output signal, some characteristic, power, voltage, or current, divided by the input. So power gain G is the power in the output signal divided by the power of the input signal. So that would be voltage times current, or voltage squared over some resistance in both the numerator and denominator. We will be dealing mainly with voltage amplification for our BJT amplifiers, and that's defined as the voltage of the output signal. So this would be our V peak or our VRMS of our output divided by the same description of our voltage amplitude on the input. So we do not compare RMS to peak or vice versa. It's V peak on the output over V peak on the input, or VRMS on the output divided by VRMS on the input. So it's that ratio. We can also define gain in terms of current out versus current in, divided by current in. So all different ways of describing gain, which is what we basically build an amplifier to accomplish. Okay. To describe important characteristics of amplifiers in this chapter, we're going to define what's known as a generic voltage amplifier. So we're going back to the concept of a model. And to do that, we're going to sketch this cute little triangle here that more or less represents some pretty complicated circuitry that we don't have the knowledge to handle yet, but we can measure and characterize and maybe look up in some specs and then appropriately utilize in a circuit. This is the symbol that's typically used for an operational amplifier type of circuit, something that we'll be studying in the future in simplified context. So everything inside of this triangle is a fairly complex circuit that nonetheless has some important characteristics that we're going to explore. Okay, so generic voltage amplifier, complex input-output circuitry that we are going to represent by a voltage source and some impedances. So two important characteristics of any generic voltage amplifier. Stuff that happens on the input side, so what your input signal sees, so it's a perspective concept here. All of the input characteristics such as input impedance are what your input signal is going to see as it looks into the circuit. So for instance, if we have a voltage signal coming in to our generic voltage amplifier, it's going to see an impedance of Z in between it and ground. So that's what the circuit sees. The input signal sees this impedance and then ground. That's all it sees. And the Z in could be the result of a lot of circuitry, but the signal just sees this as an impedance. On the other end, if we go to the output end of the circuit and we look backwards, back into the circuit, that output is going to see, again, some kind of impedance. This time it's labeled as a resistance R out, or assuming it's a real impedance, real resistance. And then it sees a voltage source, a sinusoidal voltage source in this case. And that voltage source has an amplitude that is related to the input by definition, and it's related by the voltage gain, A sub V, right up here. And that pretty much represents the whole complex circuit. So we've got an input signal that can come in, we can apply any input signal, and it's going to see this voltage drop to ground, complex voltage drop, complex impedance, and there's going to be a voltage source somewhere in this circuit that supplies an amplified signal based on our voltage gain with some voltage drop over an output resistor or an output impedance to our output, which then we'll apply to another circuit, some load, something we're going to do with it. So one of the things we will examine is what we want in terms of the output versus the input impedance, and whether we want them big or small in terms of whether or not we actually realize this entire voltage gain, and what effect we have on distortion when we actually load the circuit and insist that it provides some current. What we're going to find out is that we're going to get our best signal transfer, and we're going to realize the majority of our theoretical gain if we have big input impedance and small output. So that's a general rule of thumb for amplifiers. We want high input impedance and low output. And a way to think about this is your digital multimeter. When you're taking a voltage measurement, you want your meter to have a very high input impedance so you're not siphoning off much of your circuit current through the meter to make your measurement and thereby altering what you're measuring. If you're doing so that's analogous to your input impedance. You want that high. When you're doing a current measurement, you want your impedance very, very low so you're not introducing no voltage drop into the circuit when you measure current over your shunt resistor. So that's kind of like the output of this generalized amplifier. You want R out low, the same reason you want your shunt resistor and your meter low to make a current measurement. So let's take a look. Let's put that into practice with developing some math, put this model to work for us. Let's look at what happens when we load the amplifier, and by loading that means we put in a real signal and we ask the amplifier to give us some real current. So instead of just putting in an ideal voltage input to our amplifier, we're going to have a real live voltage source, like maybe the arbitrary waveform generator of our picoscope or other function generator, and it's going to have its own series resistance. So we'll set our input signal here, and then we're going to drop some voltage over the output resistance of that source itself before we ever get into the amplifier. So our dotted line here represents the boundary of the amplifier circuit. So we're gonna load the input with a real source that has a series voltage, or excuse me, a series resistor that will induce a voltage drop. Likewise on the output, rather than having an infinite impedance here between the output and some theoretical ground, we're going to use a real load resistor, which is not infinite, so current's going to flow. Current's going to flow in this output. So one thing to notice is we've now created two voltage dividers. Our input signal, our input voltage, is now going to divide over RA and RN. So the voltage input to the amplifier isn't going to be all a Vin like we'd like. It's going to be a reduced portion of that, dictated by the ratio of our input impedance to whatever that resistance was associated with our actual applied signal. So what we actually see in the output side of the amplifier that we're going to apply the theoretical gain to isn't Vin, it's Vin at the amplifier. So that's what Vin amp means. And that's actually only a portion of Vn dictated by our input voltage ratio, voltage divider. Now here's where having a high input impedance is our friend. If Rn, like the input impedance to the amplifier, is really big, like 10 mega ohms or more, chances are it's going to be much bigger than Ra, whatever the series resistance is of our input signal device. If that's true, then this fraction becomes almost 1, and we don't end up reducing the signal that we can apply the gain to very much. So there's a good mathematical example of why we want a high input impedance. We're not going to be sacrificing much of that input signal before it ever really gets into the amplifier to get amplified. Okay, so now let's look at the output. What we want is to get as much gain at our output as possible, but unfortunately we once again have a voltage divider working not in our favor. We've got our voltage source somewhere in the amplifier circuit that's going to act on whatever portion of our input signal gets into the amplifier. It's going to multiply it by our theoretical gain, our A sub V. There's going to be a current flow, and of course the current's going to flow, and there's going to be a voltage drop over R out, the internal output impedance of the amplifier, and then of course it's going to drop over the load. The actual voltage at the output versus ground, which is what we care about, is again only going to be a fraction of what the voltage produced here inside the amplifier, because there's another voltage divider. We only get part of that. So we're going to have to multiply our voltage produced within the amplifier output circuit, our gain times Vn amp, by this divider. But if R out is really small, like we said we wanted it to be, then this turns into a 1 again, and we recover what we would have lost in that divider. So there's a mathematical example of why we want big input impedance, low output impedance. But nonetheless, in real worlds, we don't have infinitely large and small values. Even though they can approach ideal, they typically aren't. So we're going to remember these equations and use them in some examples to see what happens to our real gain, our system gain, when we have real live inputs and loaded outputs. And then when we get to chapter 7 and we apply this to some actual real simple bipolar junction transistor amplifier circuits, we'll see this happening for real with some voltage generator inputs and then some loaded outputs. So keep this in mind. We'll see this again in some circuits you can actually build and measure. Okay, so let's define a new gain, the system gain, which is the voltage drop over our load, which we're going to say is V out, but this is V out if we actually are going to flow current, divided by V in, which again is not what actually gets into the amplifier. It's V in here. So let's see how this works. So we have a theoretical gain of 20, so A sub V is 20, so there's our multiplier in the amplifier output circuit. We have an input impedance of 10 kilo ohms, which isn't as big as we'd like, an output impedance of 200, which is probably bigger than we'd like, of course, and we're going to try to amplify a signal with a 30 millivolt amplitude on the input. That's pretty small. If any of you have worked with a picoscope, USB oscilloscope for any of your exercises in this course or in previous ones, you'll remember that 50 millivolts is about the smallest range you get, and it's often very, very noisy. So a 30 millivolt signal is pretty small. And we're going to assume that that input signal of 30 millivolts is in series with a 600 ohm internal impedance. So pretty big. So here's the signal we want to amplify, and it's going to flow and drop some voltage over its 600 ohm impedance before it ever gets out of whatever's generating it. And so here's where it's going to hit our amplifier circuit. I've dropped the triangle here, the dotted triangle for simplification. So basically the voltage at this point on the corner is what's going to correspond to V in amp. So we can make our voltage divider using Kirchhoff's voltage law or this equation. So what is actually going to get into the amplifier, so our 20 times gain will operate on, is the ratio of this resistor to this one plus that one. So rather than 30 millivolts being seen at the part of the circuit that's going to apply the gain, we only see 28.3. So we lost a fair bit, not quite 10%, but close to it. Okay, we're going to lose a little more because we're going to flow some current through this output circuit because we've only got a 1 kilo ohm load. So there's going to be a fair bit of current flowing through this. So we're going to have the opportunity to drop some voltage over this 200 ohm internal resistor, regrettably. So how much current do we have flowing? Well, we gotta see what our actual voltage source peak is. So we've calculated our V in to the amplifier, 28.3 millivolts. We're going to get our 20 times voltage gain. And so Ohm's law says our output current is going to be our total voltage, which is 20 times our 28.3 millivolt divided by the total impedance to ground, which is 200 ohms plus 1,000 ohms or 1,200 ohms. So here's Ohm's law to the rescue again. That gives us 0.4717 milliamps. So if we flow that across those two resistors, we notice that we are only going to have a load, a voltage drop over a load resistor, so a voltage at this point here versus ground, of about 472 millivolts. So if we ratio, so there's our V load. So our system gain is our V load, which is our V output, divided by our original input, what we were trying to amplify, so that's 30 millivolts. So that ratio is only 15.7 as opposed to the 20 that we were theoretically supposed to have. So we knocked down 20-25% versus our theoretical gain due to imperfect input and output impedance resulting in loading effects on both ends of the circuit. So this shows you the power of real circuits, loading, and input and output impedance on the performance of a real amplifier. Okay, so there's loading effects affecting our gain. In addition to knockdowns in theoretical gain, other problems with real amplifiers is, of course, they do something more than change the amplitude. The things we don't want them to do, like change phase, change waveform. These other changes that we never want to have are known as compliance and distortion. So ways in which something other than amplitude changes. So we've already touched on the idea of compliance with respect to our DC load line. We've calculated the maximum current voltage range over which a bipolar junction transistor in a biased circuit can operate. That's going to have some significant effects when we start sending a signal into our transistor base, and then using the signal control of collector current. The base emitter current controls collector emitter current. That's going to give us our amplification, a current amplification that we'll see through some voltage drops over resistors is going to transform into voltage amplification, an AV, voltage gain. But we're going to be limited on how much we can actually get out, the output, by our I sub C versus V collector emitter relationship on our load line, and that's known as compliance. And at the end of the day, what that says is we've got a finite range of voltages that we can actually push out of the amplifier. It's limited by the DC biasing limits. So what that's really going to mean is if we have a given input signal and we apply some voltage gain through our amplifier, which we're usually hoping to do with an amplifier, we could get a very high amplitude output that we want, but we will only actually be able to achieve what's within these two dotted lines. And that's actually defined again by our DC load line. So what we get is this chopped or clipped waveform that is very reminiscent of what you would see with a diode clipper. So instead of coming up and having a full sinusoidal signal down, we've whacked the top and bottom off, and this may or may not be symmetric. If we are operating all the way over at one end or the other of our DC load line, we'll actually chop off the entire top or bottom half of our output waveform. And that's actually a bona fide mode of operation for amplifiers known as Class B. It's actually done on purpose, but in that case you have to use two and then recombine the signals. So if you want to only have one amplifier and get your entire signal out, you want a very high compliance so that the whole signal will emerge and you won't be limited by basically your biasing capabilities. Other things you don't want to have happen: nonlinearity. You don't want the gain itself to change with anything ever. You want that gain to be a constant fixed number that doesn't change with time, doesn't change with frequency, doesn't change with amplitude of the input signal, because if it does, you're going to have multiplicative effects and you won't get a straight amplification. You'll distort the waveform and you won't have the signal you want on the output. Now, most amplifiers, especially bipolar junction ones, definitely have a frequency dependent gain. This is under the title of frequency response, so the gain varies with the input signal frequency. So your V out versus V in is not going to be the same at 60 Hertz as it is at 600,000 Hertz, for instance. A typical plot of gain versus frequency is shown here, where at really, really low frequencies we have super low gain, and it comes up pretty fast. At some point we have what's known as the half power of frequency, F1, and in the middle we have a nice stable operating region known as the midband, where the gain really is constant with frequency. And generally this midband region is where we want to operate. When we get to even higher frequencies, we have another roll off when we start losing gain as we go up and up and up. So we can design an amplifier such that this mid-band region hits within the frequency range that we're interested in using. And we certainly don't want our frequency to change as the result of amplification. As a last note, something that we'll see in Chapter 7, this reduction in gain as we go to lower and lower input frequencies and approach DC, this is the result of what's known as coupling capacitors, where we want to separate what happens to our AC signals coming into our amplifier versus the DC biasing voltages that basically allow the amplifier to work. There are amplifier designs that don't have coupling capacitors on the input. Those are known as direct coupling and in those cases we can use them for really low frequency signals approaching DC. So sometimes this gain will stay constant to very low frequencies. The circuits we'll see have coupling capacitors on the input. We'll see that when we start doing our AC models of small signal amplifiers, and they'll have this frequency response. Operate in the midband where gain is constant. Okay, last but not least, an essential characteristic to any kind of signal processing, signal to noise. When we're doing any kind of signal manipulation, especially amplification, we want a certain information carrying signal, a time varying voltage signal that conveys information, like my voice in this recording, for instance. We don't want any kind of random signals that make it impossible to distinguish the signal we care about. And signal and noise are quite often distinguished by frequency, in that signals have a particular frequency, like, say, the frequency of my voice that you're hopefully able to hear now. Noise is more or less constant over all frequencies. So it's very difficult to selectively reject on a frequency basis, say with a notch filter or a low or a high pass filter. It's very hard to get rid of because we can't selectively ground it out with a filter circuit like we learned about in AC. We can't have a nice inductor, capacitor, resonant filter that just grounds out all our noise, because it's at every frequency. So what we want to do is just simply reduce the amplitude of the noise so that we can actually interpret our signal. So it's very important to understand the differing roles of gain and signal to noise in getting a signal out of a circuit, an instrument that we can interpret, that gives us the information we need. So gain is basically, you can think of it as a brute force multiplication factor. Signal input and signal output, output over input. Signal to noise is the ratio of our information carrying signal, like our V output, for instance, to our V noise. And the higher our signal to noise ratio is, the better we can interpret our signal. This is sometimes known as fidelity or clarity or resolution. So that's truly a much more difficult task to achieve, and it's really the goal of a lot of electronic circuits, is to increase signal to noise of anything from music to a signal that's telling us information about some complex system, like the pressure in something in the refinery down the street. We definitely want to be able to interpret that correctly. So signal to noise is a concept we'll be working with in the future, especially in operational amplifiers portion of our ENET series. Okay, that wraps up our lecture and discussion of general amplifier characteristics. We will carry these general concepts forward specifically with small signal amplifiers. So we're going to take our bipolar junction transistors, take all of the concepts that we've learned about DC biasing, and now we're going to put a signal into them and actually achieve some amplification and calculate gains and look at real input and output impedances and start looking at the real effects of these kind of loads and other things we've discussed here. We will not touch on signal to noise in this ENET 130 course, but we will pick it up again in the context of op amps in ENET 140. We'll see you then.